Alright, so now that we've done just kind of a short review on Chapter 11 and Chapter 13, I am going to actually move into Chapter 14. So keep in mind that the computational parts are not going to stop. They're going to keep going, and we're going to get even more formulas and ideas. So for the first part of Chapter 14, basically what I'm going to do is explain the reasoning behind why we're doing all this, and then as we move through Chapter 14, we'll start putting more computations back into this. So Chapter 14 and 15 will be sort of combined in a sense, whereas the computations in 14 will go with all the inferences and conclusions that we need to draw using Chapter 14. Okay, so for the first part of this, we want to recall that the main reason for doing statistics is to make inferences. So really what that means is we want to draw conclusions and make predictions about a population from a sample data or vice versa. So if we're making inferences, this really just means we want to draw conclusions. Okay, and make predictions about a population from sample data or vice versa. So basically, when we're going through and doing statistics, we're collecting a bunch of data, we're analyzing it. Well, the whole point of doing that is so we can actually draw conclusions and then predict what might happen in the future. Okay? Keep in mind that when we go through and do this, there will always be some uncertainty. So there will always be some uncertainty. Okay, so you never really know what's going to happen, right? Right now, if we think about obesity, for example, we know that it's going on at an inclining rate. We can get statistics about that, and we can predict, the percentage of the population that will be obese in the future, but we don't know that's going to happen for sure. There will always be a little bit of uncertainty with this. So this gets back to kind of the beginning of the course where we're saying, yeah, we can look at things numerically, but we don't necessarily know that that's exactly what's going to happen because things can change, or maybe we could have some flaws in there. Okay, so for example, this is an activity that we would do just in class. So we did a penny activity, and I described it in the previous video, where each student was given 5 pennies just randomly, and they had to find the average year on the penny. Of course, that's totally random. Okay, we didn't know the average of the person's penny before they recorded them, but when we got through, we found out that after we took all the sample averages, it ended up being the same as the population. So anyway, let's generalize this to a bigger idea that we have talked about a little bit more in this course. It says, in general, if we pick different samples, from a population, so in general, if we pick different samples from a population, we would probably get different sample means. We'd probably get different sample means. So basically what this is saying, if you think about the simulation video the guy in Khan Academy did, he pulled a sample. When he found the mean, it was different than another sample he pulled. So maybe if I have a group, of everybody in the United States, I could say, oh, I'm going to grab these random 30 people and take their average. Well, if I grab another 30 random people, their average will probably be different, but we're going to find in the long run that eventually it would all turn out and be the same, which is kind of what that simulation video showed us. So basically what this means is, we're up here, virtually none of them would actually equal the true population mean. Okay, it wouldn't start to normalize. Let's see. Okay, so here, yeah. It wouldn't start to normalize until we looked at the samples in the long run, or looked at a large number of samples. Okay, so yeah, if we just look at a couple different groups, it's not going to look at the same as the population, but once we look at a bunch of them, aka in the long run, or a large number, becomes closer and closer to the population and closer to the normal distribution. So that's why we look at them in the long run as bigger ideas. Okay, so just to kind of recap what this looks like visually, we've talked about this before. Okay, but basically what this picture is saying is, if we say observe something on one subject, aka our sample size are smaller, we know it's going to be more spread out. But if we pull a larger sample, say 10, I guess in this, we know it's going to come closer together, and that's why our little standard deviation is adjusted and becomes smaller. So when we take more samples, it's going to suck our values in closer to our mean, making our standard deviation smaller. another little image here, and this is going to be hard to see on here because it's not in color like it is online. So if you're looking at your online notes, this will all be in color, but we can still kind of get the same general idea here. Okay, so basically, if we're looking at this, I think our population distribution would be kind of this big, more spread out one. The sample distribution would be this little one that's sucked in more. So if we went through and actually pulled a bunch of samples, I'm going to slide this up and pretend like I did. Okay, so let's say we pulled a bunch of samples. I would see that if I drew random samples, they maybe hit close to the mean, right, and with an interval with the mean, but they wouldn't all be the same. So they'd kind of spot around it, but they wouldn't be exactly the same as the mean, and that's sort of what this piece is illustrating. Okay. So that brings us to the next page. So now we're just going to emphasize that more. We're going to figure out how to do more calculations and look at this reasoning even more. Okay, so with this, I still cannot say exactly what my sample mean would be, just that it would be close to the population mean and the sampling distribution means. Okay, so I'm not going to know exactly what it is. I just know, okay, it should be somewhat close. That's why we can use that population mean to make estimates for it. Okay, so what we can do with this is look at the probabilities of values occurring. Probability of values occurring. Using what we call confidence intervals. So we're saying, okay, I don't know exactly what this is going to be, but I think it should occur somewhere in between this number and this number. So if you're in between two numbers, you're really looking at an interval. Okay, so for example, when we take a random sample, we can compute the sample mean in an interval size plus or minus 2 times, standard deviation over root n if we're adjusting for a sample, okay, around the mean. When we do this, we would predict that about 95% of all intervals computed with this method capture the parameter mean. Okay, so basically what this is saying is, if we have two standard deviations, we know that when we're within 2 standard deviations, we're talking about 95% of data. Okay, so now if we say know the sample, and we're using the sample mean to predict the population mean, which is opposite of what we're doing in 13. In 13, we're using the population mean to predict the sample mean. Now we're using some sample mean to predict something about our population mean, that parameter. Okay, we know this because of, and the reason we know the 95% with the 2 standard deviations is from chapter 11 when we talked about, I think the book calls it 65, or 68, 95, 99 rule. Okay, so we can just say, all right, we know that's true because of the 68, 95, 99, I guess technically 99.7 rule. Okay, so this prediction is really done in terms of a confidence interval. So if we want to go from a sample mean to a population, basically what's happening is I'm doing research and I'm gathering data. Let's say I want to, make a prediction about college students. So I could say, all right, I went and gathered a sample of 1,000 college students. Now I want to use this sample to make predictions about all college students in the United States. Honestly, for me, this is a more realistic version of statistics because usually we do start with some little sample of data and move to making predictions about population. In 13, we're doing the opposite, starting with population, predicting samples. That doesn't happen nearly as often. Okay, so anyway, when we make these predictions using the sample mean about the population, this is really done in terms of what we call confidence intervals. Okay, so I'm going to define this a little bit more. Okay, so a confidence interval, interval is a range of values with an associated probability, or what we could call a confidence level. And really this just means how sure you are the value could occur in the given range. So this just means how sure you are that the value could occur in a given range. So this probability will basically give a numerical value to the chance that the interval contains the unknown population parameter. Okay. Or the unknown sample statistic, depending on what you're doing. Okay, so if you're using the population information to make a prediction about the sample, then what you would be doing is this. You'd be looking at the confidence interval or the chance that the unknown sample statistic would fall in between two values. If you were using the sample information to make predictions about the population, that's what this is, then you would be looking at the probability the population parameter is in there. So for example, if I said the average number of hours that a student, college student spends playing video games is 2 hours. Now make a prediction about the sample, say I pull some sample from this population and make a prediction, then I could say, oh, I'm 95% confident that, that sample statistic will fall in between this value and some other value. So I'll do examples of this, but that's kind of the idea behind that. Okay. So anyway. When you go through this, so if you're making an estimation, whether you're going from a sample to a population or a population to a sample, do you think that it's going to be perfectly accurate if you're making the estimate? No. So yes. Yeah, it's an estimate, right? So it's an estimate. It's not going to be perfectly accurate. So we have to think about adjusting for that. So that's what we're going to look at next. How do we adjust for this lack of accuracy? Okay, so it turns out it's not going to be accurate, but what we can do is take that into account and estimate what we call margin of error. So we say, okay, we're making an estimation. I know I'm going to have a little bit of error in there. We'll call that a margin of error. So here, margin of error is just the accuracy of our guess for the parameter for statistics. Okay, if we're making a guess for a parameter, we'll be using, sample data to make the prediction. Okay, of course, if we're estimating statistics, then we'll use the population parameters to do that. Okay, so formulaically, what we have for a confidence interval. Okay, so if we just want to find a formula for the confidence interval computationally, what that looks like is our estimate, so whatever our estimate is, plus or minus the margin of error. Okay, so we're going to say our estimate is this value, and it's going to be within whatever this little margin of error is, and this is what helps us calculate that confidence interval. Okay, now just to get some notation in there, if we're using population parameters to estimate, we should say our sample statistics, we would have the confidence interval represented as. Okay, so here we're making an estimate about x bar, the sample mean, that's what we act like we didn't know. Then we'd have plus or minus the z-score times sigma over root n for the margin of error. So that's if we're using population to make a prediction or an estimate about our sample statistics. Okay, and then let's see. We're using sample data. Oh, sorry. Getting some notation over this. We should add population parameters. Oh, sorry. This would be an x. So right here, we're using population parameters to estimate our sample statistics. We have this, yeah, plus or minus that. Okay, now up here, if you're using sample data to estimate the population parameter, what you have for that one is x bar, our sample data, plus or minus, and then we would have the z and sigma over root n. So I mixed these up a little bit. They're right in your online notes, but this one right here should just be a sigma. Okay, so I better recap that a little bit. So if we're using sample data to make an estimate about a population parameter, we have what we're using to estimate, so that's whatever piece of information we have. If we have the sample data, then we would have X bar. And then this is just our adjusted standard deviation for if we're looking at the sample. Okay, down here, if we're using population parameters to estimate, then we would just have X, our data value, plus or minus Z times our sigma there. Okay, and then just take note that usually what we're going to use is this first equation. So usually, logically in statistics, you're usually going to use that sample value to make predictions. So typically this guy right here is what we're going to use, but we can take note of both of them. All right, so next I'll do the chapter 14 part 2 video. For that, we're going to take all of these words and formulas and reasoning and actually put them into more computational situations. Okay.